So why does a current flow in a potential difference? Now, this is something that puzzled scientists way back, and it still puzzles us. But we have an answer. It's called the principle of least action. I'm not going into this and the Lagrangian, but on the whole, I would like to say all configurations in this universe try to reduce the potential energy. All of them. You have Earth, you have an object, it's at height, some h, the gravitational potential energy between them, considering both of them as a system, is mgh. Now, of course, when the external force keeping the block above is removed, the block finally falls down and the potential energy is reduced to zero. And the block doesn't move horizontally if if it's an ideal horizontal plane, it doesn't move because all these planes are at the same height from the center. Not It doesn't just happen for gravitational potential energy. It happens for all kind of energies. You have a positive charge and you have another positive charge. The gravitational potential energy between them is kqq by, assume, equal charges by r square, and you leave them. These charges go on till infinity. This r is reduced to infinity, and upon infinity square is zero. Minimum potential energy. You have atoms. You have atoms. See, if you have two molecules, we're not talking about atoms here. We're talking about just molecules. If you have two molecules, then this is the graph for the potential energy and the distance between those molecules. It goes something like this. Now, let's say this point is R naught, where the potential energy is the minimum. You know the force potential energy, of course, is F dot dx minus, talk about internal forces, conservative. So F can be written as minus du by dx, or of course here we chose it as R. Let's rename it as R x. So the force is zero, of course, when the dv by du by dx is zero. And this is basically the formula for the slope. And when is the slope zero in the whole diagram? Here. Here's the slope zero. And this is when the potential energy is the minimum. And this is when the force on another molecule by a molecule is zero. That means there's more stability when the potential energy is the minimum. If we go to the molecule, to take another molecule and go nearer than this R naught, you get a repulsive force. And sends it back. Why? Because you see the slope is negative, this whole thing is negative. Negative and negative makes positive, so the positive force acts essentially. And the positive force is defined, of course, to be a repulsive force. While here you have a positive slope, positive and negative force means basically an attractive force. It basically, like, it depends on how you define the R vector, right? But anyways, because if you have a force, this is a particle, and you have a force, and this is how you define R vector, then of course it's minus of R vector or minus F1. That's how you get a attractive force if this is another particle. But anyways, let's not go too much into the technical details. Now what happened was Let's talk about conventional current. So it was a glass rod and it was rubbed with silk or some kind of a material. I don't remember particularly. And there was this man. It's called the founding father of America. Looks more like a woman. I'm sorry. But it was the founding founder of America, Benjamin Franklin. My father knew him as a statesman, and I knew him as a scientist. And you know, like 4 years back, and we were like, no, he's a statesman. He was like a statesman. I was like, he was a scientist. So, anyways, so we have a glass on it was rubbed with silk, and this man, Benjamin Franklin, noticed that if you touch this with your fingers, then you get a shock. So he thought maybe there was some kind of an invisible fluid, the some kind of an invisible fluid in the atmosphere or something like that. That got to this glass rod or glass tube when the silk was rubbed off with it, and because that fluid maybe was less amounts on the hand, so that fluid got from this glass rod to our hand, and so because we had less of that fluid, our hand was called negative, and because the glass had more of that fluid, it was called positive. It's basically if both of them had the same amount of fluid, they were called neutral. If this had more fluid, it's called like plus, and if it has less than the neutral of the system, it's called minus. That was the way like current was reduced, and he thought that the current moves from this plus, like plus means where there is more, and minus means where there is less. So he thought the current moves from plus to minus, from where there is more to where there is less. It's similar if you connect uh like two tanks by a pipe, and they'll keep moving till the extras or the extra height here is equal to the extra height here. The negative height here, what I'm talking about. See, of course, you know the formula is h rho g, and for the horizontal levels, it has to be same, and it's not. So the fluid will keep on moving, and the fluid will keep on decreasing on this side till the horizontal level becomes same on both sides. But anyways, what we finally found was after the discovery of the electron was that when we rub this whole thing, it of course got some charge. Of course, we defined it as positive because of this guy. We defined it as positive because the electrons were removed, and there's nothing wrong in that. We defined as positive as the electrons were removed. The way the positive was designed is something different, but we call it positive. We call protons negative because of the him. But what actually happens is that our hands are neutral, and the electrons from our hands jump. So it's not that the fluid comes from the glass rod, it comes from a hand. And there's a difference. But there's nothing wrong in calling the protons positive. Though it lacks, if you assume the invisible fluid to be electrons, it does not have an excess of those fluid. It actually has a lack of that fluid. Our hands have that fluid, which is if we assume to be an electron. But anyways, so we of course made batteries in a way that like we assume the conventional current to be opposite to the direction of the flow of electrons. Now, if I'm not getting to the question, why does a current flow in a potential difference? So, what is potential? Potential is basically the change in potential energy actually, not work. It is work essentially, but anyways, change in potential energy divided by the charge. It's the change in potential, of course. You have the change, you can assume the initial to be anything. and the final to be such that the difference comes out to be this whole thing. Now let's assume you have a so one another thing is that the electrons move from a lower potential to a higher potential, but they always move from a higher potential energy to a low potential energy. What do I mean by this is, let me try to tell you. Let's assume this is a battery. You need some kind of a resistor, otherwise the current will be like infinite. We have need some kind of a resistor. Like, see this. I have a bulb. That's it. And let's assume what happens are in the battery they are oxidizing, reducing the actions that causes uh, electrons to be like forced through this wire for the metal inside the battery to be oxidized, and the battery dies when the whole metal in the battery gets oxidized. So like let's assume there's some kind of a positive, not positive, positive is here, some kind of a negative charges that form here, some kind of negative charges. Of course, the negative charges come from the battery, from the whole wire, not just the battery. But let's assume there is a battery. Just for simplification sake, let's assume the all the charges on this side is essentially combined just one big bomb of like electric charge. I know it's a simplification, but it gets easier. And there's a small another electron. Similarly, of course, positive charges do not move, but we'll just assume a lack of electrons. So there's this one big bob of positive charge. Now, if you calculate the potential of this small electron with respect to this big bob of charge, uh, you know, it comes out to be k q by r square. Let me assume q to be negative, a q to be positive as in magnitude. So minus kq by r square, where q is always positive and r is of course positive. The whole thing is negative. Minus kq by, not r square. I'm sorry if I used the term r square. It's minus kq by r. And here the potential is kq by r. So it seems like the electron is moving from a lower potential, that's minus, to a higher potential, kq by r. Seems opposite. But what really happens is, from the potential energy is the potential into the charge. So you multiply the charge of an electron. Charge of an electron is negative. Let me take E as positive. So the minus will come in front and minus will make it positive. And the minus will make it negative. So actually, if you talk about in terms of potential energy, the electron actually goes from a higher potential energy, the positive potential energy, to a negative potential energy, right? So the whole thing is a very lexical thing. Like you have the charges, and the positive charge is defined in such a way that it goes from a higher potential to a lower potential, and if one thing goes from a higher potential to a low potential, the other thing must go from a low potential to a higher potential. Yeah. Electrons go, let's talk about electrons, of course. There are no positive charges, but of course, we have protons, but they don't move. Just talking about electrons, they go from a higher potential energy to a lower potential energy, and that's it. So when there's a difference in potential, there's a difference in potential. What is potential? This thing called kq by r. Of course, I assumed it for unit charges. Of course, if it's a spherical blob of mass, then it's right. But if it's a oval blob of mass, not mass of charge. But anyways, and this thing for all the electrons, because basically things move from a higher potential energy to a low potential energy, and that's what's causing a lot of things in. And basically, it's some kind of related to the principle of least action, which is the integral of the Lagrangian with time, something like that, if I remember correctly. Lagrangian is defined as the kinetic energy minus the potential energy. And the whole thing is called action. It has to be minimum. And it's not just related to configurations. Even when light goes from one medium to another, it follows the principle of least action. One thing you might ask is, oh, okay, so this whole thing has to be minimum. This thing has to be minimum. So L has to be minimum. For L to be minimum, T has to be maximum. What? Potential energy has to be minimum. But so yeah, it is an integral. So you have to calculate integrals by integral. In this way, if mass drops from the like surface to the earth, then initially it had potential energy and the kinetic energy was zero. So Lagrangian was negative and the action was negative. And as it moves on, the kinetic energy finally increases and the Lagrangian becomes positive and the action increases. But of all the ways possible, it is the only way for the whole paths to have the least action. But first, we're talking about the whole path. So we're not talking about just some kind of dt times. But anyways, that was it. That's it. That's it. Not talking about pipes and all that. That's basically some childish nonsense.